Welcome to SS2 Further Mathematics, Term 3, Week 9. Not all equations can be solved with exact algebraic methods. Equations like x superscript 3, x, 1 is equal to 0 or cos x equals x have no neat closed-form solutions. Numerical methods allow us to find approximate solutions to any desired accuracy. The Newton-Raphson method is the most widely used and fastest converging root-finding algorithm. By the end of this lesson, you will state and arrive the Newton-Raphson formula, apply it iteratively to find roots to specified accuracy, identify when the method may fail, and answer WAEC further mathematics problems. Let us begin. Before applying Newton-Raphson, we need to locate the root approximately. Graphical location, sketch y equals f(x), and identify where the graph crosses the x-axis. Change of sign, if f(a) and f(b) have opposite signs, one positive, one negative, and f is continuous on, then by the intermediate value theorem, there is at least one root in a, b. This is the sign change method. Decimal search, bisection find the interval where the sign changes, systematically narrow the interval by bisection, always choosing the half interval containing the sign change. Bisection example, f(x) equals x superscript 3, 2x, 5, f(2) equals 8 minus 4 minus 5 is equal to minus 1, negative. f(3) equals 27, 6 minus 5 is equal to 16, positive. Root is between 2 and 3, f 2.5 equals 15.625, 5 minus 5 is equal to 5.625, positive. Root is between 2 and 2.5, f 2.1 equals 9.261, 4.2 minus 5 is equal to 0.061, slightly positive. Root is between 2 and 2.1, f 2.09 is almost equal to 9.129 minus 4.18 minus 5 is equal to minus 0.051, negative. Root is between 2.09 and 2.1. The bisection method is slow, one decimal place per 3 to 4 iterations. The Newton-Raphson method is much faster. Geometric derivation of Newton-Raphson, start with an initial approximation x near a root. Draw the tangent to y equals f(x) at the point x, f(x). The tangent line will cross the x-axis at a point x, which is generally closer to the root than x. Repeat the process. Draw the tangent at x, f(x), find where it crosses the x-axis, call this x2, and so on. Equation of tangent at x, f(x), y, f(x) equals f(x), x, x. Setting y equals 0 to find where the tangent crosses the x-axis, f(x) equals f(x), x, x. X equals x, f(x) slash f(x). Newton-Raphson iteration formula, x underscore n plus 1 equals x underscore n, f x underscore n slash f x underscore n. This is the Newton-Raphson formula. Convergence, near a simple root, the Newton-Raphson method converges quadratically. The number of correct decimal places roughly doubles with each iteration, compared to bisection which gains 1 bit per iteration. Starting from 1 decimal place accuracy, you reach 10 decimal places in about 4 iterations. Worked example 1, use Newton-Raphson to solve x superscript 3, 2x, 5 is equal to 0 starting from x equals 2 to 4 decimal places. f(x) equals x superscript 3, 2x, 5, f(x) equals 3x superscript 2, 2. Iteration, x equals x, f(x) slash f(x) equals 2, f2 slash f2 equals 2, minus 1, forward slash 3, 4, 2 equals 2, minus 1, slash 10 equals 2 plus 0.1 is equal to 2.1. x2 equals 2.1, f 2.1, slash f 2.1 equals 2.1, 9.261 to 4.2, 5, forward slash 3, 4.41, 2 equals 2.1, 0.061 divided by 11.23 is equal to 2.1, 0.00543 is equal to 2.09457. x3 equals 2.09455 f 2.09455 slash f 2.09455. F 2.09455 is almost equal to 0.000096, very small. X3 is almost equal to 2.09455. The method has converged. Root is almost equal to 2.0946 for dp. This took only 3 iterations to converge to 4 decimal places, much faster than bisection. Worked example 2. Solve cos x equals x starting from x equals 1 meridian. Let f x equals cosine x, x, f x equals sine x, 1. X equals 1, cosine 1 to 1, / sine 1 to 1 equals 1 minus open parenthesis 0.5403 minus 1 close parenthesis divided by open parenthesis minus 0.8415 minus 1 close parenthesis is equal to 1, minus 0.4597, / minus 1.8415 equals 1 minus 0.2496 is equal to 0.7504. x2 equals 0.7504, cosine 0.7504 to 0.7504, / sine 0.7504 to 1. Cosine 0.7504 is almost equal to 0.7315, sine 0.7504 is almost equal to 0.6818. x2 equals 0.7504, open parenthesis 0.7315 minus 0.7504 close parenthesis divided by open parenthesis minus 0.6818 minus 1 close parenthesis is equal to 0.7504 minus 0.0189, / minus 1.6818 equals 0.7504. 0.01124 is equal to 0.7391. x3 is almost equal to 0.7391. Root x is almost equal to 0.7391. This is the dirty number, the fixed point of cosine. Worked example 3. WAEC style show that x superscript 3 plus x equals 10 has a root between 1 and 2. Starting from x equals 2, find the root to 3 decimal places. F x equals x superscript 3 plus x, 10. F 1 equals 1 plus 1 minus 10 is equal to minus 8. Negative F 2 equals 8 plus 2 minus 10 is equal to 0. X equals 2 is actually the root. Let us try x superscript 3 plus x equals 8. F x equals x superscript 3 plus x, 8. F 1 equals minus 6 less than 0. F 2 equals 2 greater than 0. Root between 1 and 2. F x equals 3x superscript 2 plus 1, x equals 2, 2/3, 4 plus 1 equals 2 minus 2/13 is equal to 1.846, x2 equals 1.846, f 1.846 / f 1.846 is almost equal to 1.846 minus 0.268 / 11.23 is almost equal to 1.870. x3 is almost equal to 1.869. Root is almost equal to 1.869. The Newton-Raphson method can fail or produce unexpected results in several situations. Failure case 1, flat tangent. If f x_n equals 0 or very close to 0 at some iteration, the formula produces a division by 0 or a very large step, the method diverges. Failure case 2, poor starting point. If x is far from the root, or if the curve has features, inflection points, steep sections near the root, that cause the tangent to overshoot, the method may converge to a different root or diverge. Failure case 3, oscillation. In some functions, the iteration oscillates between two values without converging. Precautions. Always confirm the root lies in an interval by checking sign change. Choose x as close to the root as possible. Use graphical or tabular search first. Verify convergence by checking that x_n plus 1, x_n is getting smaller. Staircase diagram / cobweb diagram. used in iterative methods to show convergence or divergence graphically. Draw y equals x and y equals g, x, for the iteration x underscore, n plus 1 equals g, x underscore n, the intersection gives the root. Convergence conditions for x underscore, n plus 1 equals g, x underscore n converges near a root if g, root 1. WAEC Further Mathematics, always show all iterations clearly in a table. State when you have reached the required accuracy. When consecutive iterations agree to the required decimal places, mention the convergence criterion f, xn, tolerance or x underscore, n plus 1, x underscore n, tolerance. Key points. Numerical methods are used when exact algebraic solutions are impossible or impractical. Root location, sign change in f, a, and f, b, implies root in a, b, intermediate value theorem. Newton-Raphson formula, x underscore, n plus 1, equals x underscore n, f, x underscore n, slash f, x underscore n. Convergence, quadratic, very fast, near a simple root, correct decimal places roughly double per iteration. Method steps, identify root interval, compute x from x, compute x2 from x, continue until consecutive values agree to the required accuracy. Failures, f, x underscore n, equals 0, flat tangent, poor starting point, overshooting to wrong root, oscillation. Always show working in a table with x underscore n, f, x underscore n, f, x underscore n, x underscore n plus 1. WAEC on Newton-Raphson, show root exists in given interval or sign change, write the formula, carry out 3 to 4 iterations, state the root to specified decimal places.